Okay, let me start now with the first lecture. You can download the material of today from my study. Let me open the file, and the lecture of today, or the topic, the first topic, is looks like. Let me see. So let me open, if I am able to open. Also, yeah, exactly. Yeah, it's a shame I didn't find the original manuscript, but I hope that nevertheless, I don't know if this is, it's not so nice. Should be better with the lateral camera, but it doesn't matter. No? Let me start. Let me start the course with an example. Why with an example? Because I would like to start with something concrete in the sense to show you what a dynamical system is and what dynamical system could be. Not only, look, we have a system which we know from electrotechnics, and we have some questions, which looks like possible question in exam. Of course, at the beginning of the course, to start with the question of the exam is a little bit stupid, of course, but could have also some advantages. At least we can sketch a little bit the structure of the examination, topics. Anyway, of course, we will see many things. We will see different topics, not only this question, but at least we can see an introduction to possible topics and insights and an examination frame, let me say. Of course, the exam I will consider an examples a little bit more, I don't want to say complicated, but more articulated. But let me start. Look at the scheme, electrical scheme. This is an RC circuit. Why the scheme in dynamical systems? Because the scheme or the system, about the word system, I will come back later. I will not use a formal definition because the formal definition came from system theory, extremely complicated, extremely formally complex. I will try to explain the concept of system using just words without mathematical formalism. Isn't a system? Yes. We will see later what a system is. Is it a dynamical system? Yes. Why that? This you know better than me probably. The reason is I can describe the system using differential equations or using a differential equation. One. We will see why one. When we are using the differential equation, we are speaking about dynamics. Why that? Because if you remember from electrotechnics, forget at this moment the differential equation. If I have an input, U input, in the battery, the voltage on the capacitor will change over time, even though the battery is in a constant value, 12 volt, 5 volt, 15 volt, it doesn't matter what. Everything, let me say at this moment, everything, then I will be more precise, will be a function of time. Look here. Also, your input could be a function of time. But if it's not a function of time, it's a constant, the value, or better to say, the voltage on the capacitor, you see the current I, the voltage UR on the resistance, they are a function of time. When we have a variables, when we have a something, let me say something, this general word, which change over time, we say that we are in the presence of dynamical systems. System, I didn't tell you at this moment what is the meaning of system or the systems, but we will see a little bit later. It's connected in our context with the concept of states, state variables, or simply states. Let me go ahead, trying to introduce the concept of systems in our course, I would like to say, analyzing and answering, of course, the question 0, the question 1, the question 2, the question 3, and then, of course, we will see more in general some considerations. Question 0, Q.0, indicate the states, or state could be one, of the system, justifying the answer. As I told you, the concept of the system is related to the concept of the state. Look at the answer 0. We can see here. The state in this system here, in this circuit, if you don't like at this moment system, you can go to the circuit. The circuit is in the system, of course. Roughly speaking, everything is in the system. A political system, for instance. But in our case, the system is basically defined, or we can understand the word system in the context of dynamical system, at least in our fields, if you read the answer 0. The state is the variable UC of T because the energy which we have in the system is the electrical one, or electrical energy. This means in our case, probably is something easy to define the system, or to understand the system, what the system is. I didn't define with the formal definition, def, dot, blah, 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 blah. But I try to give you concept. If you read the answer 0, we can understand now a little bit what we can guess what a system is, or at least in our context. In a system, a dynamical system to be more precise, is something in which we can localize, we can see energy. In this sense, it's not necessary to speak about the circuit. It's not necessary to speak about in a car. It's not necessary to speak about a thermal system and so on. A system of a process. No? I don't want to use many times the word system. A system is something which I can see, I can localize, I can somehow describe using the energy. Now, what is the energy? We have seen in different courses, also from gymnasiums. The energy, in our case, is not only the electrical energy, as in this case here, no? Electrostatic energy, no? Or let me say electric energy. In our dynamical systems, and we will see together really, the energy is everything, again this word, everything, which I can store. Example, in order to understand. Here is easy to understand that I can store load in the capacitance, the voltage. We have seen in Mare, no? The voltage from 0 to 12. I can store this voltage, and the voltage reflects the energy. We will see exactly now. But if you think, we will see together. No? We will see together. If you think about the COVID system, COVID. But so this system is a dynamical system because we can see, we can think about the energy also in this sense. But of course, it's a pseudo energy because it's not the physical energy which we learned in high school, electrical, electrostatic, electromagnetic, kinetic, what we learned, potential, and anyway, the physical energy. In this case, we can think that in such kind of process or a system, what really change, what the energy is, what we can see as possible element which can be stored are the infected people, the number of the infected people, and the number of the susceptible people. For instance, more, we can also consider more compartments because they change over time the number of infected, the number of susceptible, and generate, for instance, dynamics. Dynamic means oscillations in these two groups. If I consider just two groups, but we can consider also more than two groups, more than two states, to describe how let me say, the dynamics change. Let me do an easy example, probably. I will present here in the model, the bank model. In the bank, we can consider the liability, money, liability, you understand liability? The money which is belong to me, but is in the bank. I have in the car, but the money belong to me, but I don't have money here, it's in the bank. The name is liability. This is a state. Why that? Because I can accumulate the money in the bank, even though I don't do anything, because of the interest. The other model, the other state, which can be used to define or to understand, to analyze the bank, is the assets. For instance, also other elements can be, other states can be considered. Assets is everything which represent properties and title for different forms. Basically, for us, everything can be cumulated, in the sense also wasted, can be used as a concept of energy which change over time to describe, to control at the end the system. Here, in our case, it's easy, because we know that the voltage you see can be stored in the capacitance, or I can let me say transform this energy you see represented by reflected by you see in the thermal form through the resistance. This means we can understand that UC can be seen as a possible state because reflect exactly the energy in the system. Look at these calculations here in order to be more clear, because the calculation helps. I don't know if you remember in electrotechnic, this expression here in the middle represented the energy which I can associate to the capacitance. To the capacitance. 1 divided C or the capacitor, as you want. Better to say capacitor, no? The capacitance represent the physical characteristic of a capacitor. How I can demonstrate this? I don't know if you remember the definition of the energy is the integral of the power. Again, the integral is an extremely important concept in this field, because in particular speaking about the energy, because the integral is in a function which indicates the storage. Do you remember in high school? The integral is the sum. Sum is something like I can use to accumulate 1 plus 2 plus 3 plus is the integral. Now I don't know if you remember in high school, no? The surface and the curve integrated from starting from 0 bis 1 is the surface under this curve we have in a curve. This means the integral reflects the energy because it's an operator which indicates this storage effect. We can see that the integral of the power is the energy. The integral of the power can be seen in our system as the integral of the current. We can see here the current, which multiply, you see, our state variable, because we will see that using UC, I can exactly demonstrate that the energy is this expression here, and we can see that the energy is directly connected with this variable here. Energy, state, they are basically strictly connected, algebraically connected. Look, integral of the current multiply, you see we have just one current here. And we can see that if you remember by Mare, the UC is C times, the current in the capacitance is C times the derivative of the voltage of the capacitance or capacitor. Look, and we have this expression here. It's easy to see. Just replacing the definition of the, let me say, of the, the characteristic of the capacitor. No, the current in a capacitor is C times the derivative of the voltage in the capacitor. It's known, no? This one, clear. Now, look, if you remember in math 1, the integral of the function multiply its derivative is 1 divided to the function square. I don't know if you remember this rule. It doesn't matter. It doesn't, this is not so, at this moment, it's not so extremely important, but it's easy to remember. The integral of x multiply the derivative of x is 1 divided to x squared. If you do the derivative of this, you realize that 2 times divided 2 is 1, x multiply x derivative. Look, why I put it this one? Because the integral was calculated between 0 and t. Assuming that at the beginning, at time equals 0, the voltage is 0, I can demonstrate this. Here, I didn't wrote everything in the sense, assuming that the voltage is in the capacitor at time 0 is 0, but now I can justify this expression if at time 0 UC equals 0. Basically, this expression here is exactly what I told you at the beginning, assuming this condition. Now, why this slide? Because the idea is to tell you what a system is, and the dynamical system to be more precise, and it's an entity, is something which in which I can see the energy, and in order to describe this energy, I will use an important concept which is strictly related to the energy, and the concept is state variable or the state variables. If I have more than one energy, in this case we have just this electrostatic energy. We say that this way to proceed is this. We say that is in a state space model. This means we will see that the state is useful to build a model, which basically is a differential equation, which we know from electrotechnics. In fact, look at the answer 1, which is related to the question 1. The question 1 is build the mathematical model, state space model. State space model means based on the state. Meaning, look at this sentence here. Kirchhoff, electrotechnics, U input equal UR plus UC. The balance on the circuit, easy. Can be written U input equal R multiply the current plus UC. Why this transformation, this change? Because if the idea is to write the model using the state space, I need to express the Kirchhoff balance, which is here, as the function of the state, you see, and more important, in the equation should appear the derivative of UC. What is the derivative? If you remember in high school, if you remember in math, the derivative is the changes. That's justify also somehow the word dynamical, changes, derivative. I don't know if you remember in high school, the derivative represent the changes. This means from this equation here, now, considering again that the current is the function of the derivative of UC, which is our state, I can plug in this expression here, and what I have is this one. Should I slow down to clarify? No, I don't think so. No, it's plug in. It's difficult. It's extremely easy, no? But conceptually, it's extremely important because if we understand this equation here, just using this plugin in Ohm law, starting from the Kirchhoff law, basically everything is consequent in which sense? This equation here, the Kirchhoff balance, is an energetical balance. You remember, dynamical systems are connected with the energy. The energy is connected with the state. This equation here, you should not wonder why I'm starting with this equation. But this equation is energy balance. If you multiply left and right this equation, you have the power in input equals the power, let me say, which I lose on the resistance plus the power which I store in the capacitor. I don't know if it's visible. Why Kirchhoff is this law represents the energy balance. Because if I multiply by the current, it's a power balance. If I do the integral of this equation, is an energy balance. The energy in input equal the energy which I lose in the resistance plus which I store in the, for instance, in the capacitor. Look, when we have this, now please pay attention 1 minute on the last equation of this slide. I commented this equation with the word state space model. Extremely important. Easy, but conceptually extremely important. Mathematically, what I did here, I considered this equation here, which I commented in detail where the equation comes from, starting from the Kirchhoff balance with this energetic balance and so on. But this formalism, or this form, is extremely important because says, very. Why doesn't it work now? Here. No. The changes, the derivative equal changes we can understand. One question. It's too difficult what I have tried to explain, but too easy. If it's too easy, no problem. I can speed up, I can tell you something more complex. It's okay, you can understand me. Question.
I think it's doable what you explain, but it's hard to read.
Exactly. But did you download it?
Yeah, it's uploaded, but it's like hard to.
To understand my calligraphy.
Yeah, it's possible, but like listening and trying to,
Yeah, so I know that. Also, my wife says the same. My wife is this woman which you see at the beginning. Yeah. Now, okay. But how I can solve this problem? Question me. I can clarify what is written, what is the because nevertheless I can really redo from the beginning, but I don't know if this helped because the calligraphy reflects. But please stop me.
Once I do it, like by computer, then I can understand the rest of them. I guess.
But stop me anytime. But we are really, if in the course we have 4, 5 students, no problem for the course, no problem also for the examination, because I think the level of the communication really can be very high. I would like to say, if you ask me, I mean, if I have 100 students, I say please don't ask, because if everybody have right to ask one question, we cannot do the lecture. But here, really, any question, if this is the dimension of the course, no problem. I can offer, really, question anytime. Now, there is a little bit question. Which, please. Auf Deutsch, schon mal.
Ist das ein C eigentlich, dabei der Output-Spannung praktisch? Oder genau, und genau, aber.
C represents the capacitance.
Nee, aber ist das ein C?
Okay.
Ja. Also,
C. But I think this is the nomenclature which used also Maren, the course in electrotechnic. C is C.
Yeah.
What is different what is different is this final equation. Because here, in my course, in the dynamical system, we state the balance, the energetical balance in this form, and this means what change in terms of state, which represent what change in terms of energy, equals the energy or the states and the function of the state plus the input. I mean, think about the bank system. In the bank system, I told you one possible state is represented by the liability. Liability is the money which belongs to me, but is in the bank. This is clear to everybody. Now, this money in the bank, which belongs to me, changes for two reasons, for two causes. I put money or I withdraw money. Your input could be positive, if positive means put money, invest money. Negative, if I withdraw on the bank money. Your input could be positive, could be negative. 1 divided RC, the bank represents the tax, which I have to pay, if I have to pay, if I put money or if I withdraw money. It's a constant, which is there because probably, depends. For instance, you have a Sparkas, but if I take money from another bank, I have to pay some tax, something like that. But the liability, this means the money which is in the bank changes not only if I put or if I withdraw money. At this moment, don't think about RC. Change depending on the liability itself. Why that? Because in the bank is a dynamical system because I receive interest, which depends on the liability which I mean, depends in which sense. We have a percentual, which is basically reflected by this element here, 1 divided RC. But of course, the changes depends, of course, of this 1 divided RC, the percentual, but depends how much money I have. If I have a lot of money, I will have a big change, which depends on the states itself and depends on what I'm doing. Yes, it's similar. The voltage, the changes of the voltage here on the capacitor depends on the level of the voltage and the input. I don't know if this analogy with the bank can help. And the bank system, in terms of liability, is this one. I mean, the bank is a little bit more complex because we don't have minus here, we have a plus. I will clarify when I will consider the bank system. Because the bank system, we will see, is an unstable system. Because if it's not unstable, I don't put money in the bank. It's enough to put money, to maintain money at home. If I don't have interest there, why I have to put money in the bank? But this we will see together. Second slide, probably here a little bit more clear, but stop me if it's not clear. I put it again, this state space model. Again, the state space model is represented in this form because the idea is to describe the changes of the energy in terms of state variable or state variables. In this case, you have just one energy as a function of the state itself, we can see here, plus, in this case, plus because the system is linear. About linear, non-linear, we will see in the next lecture. What I am doing in input. Question number 2. The question number 2 says build matrix A, B, C, M, D, considering as output you see the state. And then after that, you are. Now the question is a little bit strange because what is A, B, C, and D? I will clarify in 1 second. Let me see if later I don't have. What is the matrix A? What is the matrix B? In this case, we are not speaking about matrix because we have just one state, UC. Basically, in the normal form of a linear system, about linear system, we'll tell you a little bit later, but probably you remember in math, no? The linearity, when basically the states, now in our cases, the input appear linearly. This means not squared, not with the root. They are not multiplied by the input. The input appear also not squared, just telling you about the linearity. The matrix A, or the parameter A in this case, is the matrix, or in this case, the parameter, which multiply the states. Later, I will show you a little bit. It seems that I had, but I don't have it. It's a shame. I will tell you later. The parameter A is the parameter which multiply the state. This means, in this case, in a parameter, but could be in a matrix when we have more than one state. We will see in the second example next time, this year, in which the matrix is, we have two states, and then we speak about matrices. Let me go ahead with this easy example again. The matrix or the parameter here, B capitalized, A capitalized, is what multiply the input. Just, it's extremely easy. Now, important concept today. If I have a system, a dynamical system, I can choose to observe, to monitor, to describe a variable which plays a role in my system. For instance, the state, or for instance, any other element which I can see here, the current, UR, everything which I want. How I can describe? As for the dynamics, we can see here the derivative of UC is a function of UC and the input. Also for the output, the convention is to express what I want to describe. For instance, UC is a function again of UC, we can see here, UC here, plus as a function of U input. I don't know if it's clear what I intend to do. UC and U input are the element to describe the variation of the energy, the variation of the state. Also, in an output equation, what I want to describe, in this case UC, is the function of UC and U input. This means if UC is what I want to describe, trivially, I would like to say that UC is equal to UC. This means the matrix Cm, we call the matrix Cm the matrix which multiply UC, in this case is 1, and the matrix D, or the coefficient D, is the element which multiply UN. This means we have the matrix Cm and the matrix D already localized here. Look here. If I am asking about the output UR as a function on UC and U input, it's easy to see that Cm is -1 and D is 1. Why that? The explanation is here. Again, the idea is to fix the idea. The idea is to express an output, it doesn't matter which one, as a function, again, of UC and UN, U input, excuse me, in order to be consequent with this expression here, in which the derivative, the changes of UC, we can see is a function of UC and U input. Why Cm is -1 and D is equal 1? Look at this equation here. UR is equal R multiply the current, load. But the current and the capacitance, because we have just one current, is C multiply the derivative our state. The goal is to obtain on the right part as an expression of UC and U input. But it's easy because the derivative of UC with respect to the time structure is here. If I plug in this expression, which reflects our dynamics here, I have this expression here, which is easy to see if I do the multiplication. CR multiply everything which is inside the bracket. We have minus UC plus U input. Now we can see why at the beginning I told you Cm, this matrix Cm equal minus 1, the matrix D is equal 1. I think this is difficult. It's just plug in, nevertheless, in order to obtain an expression of my derivative of UC, which we have seen before, as a function of UC and U input. And if I want to observe, if I want to describe, it doesn't matter what in the circuit in this case, also in this context here, I have to express my variable, UC in this case, UR in the other case, as a function again of UC and U input. Because everything changes depending on the state, you see, and depending on the input. This is the idea of this state space model. Question 18, Q3. Build the block diagram. I think this is easy. It's from the course of actuator. I tell you nevertheless. In system theory or in our dynamical system, very often we use again this block diagram language because the connection between the signals, the connection between the element of the system is more explicit than, I don't know if it's more explicit, in my opinion, yes, than this expression here, which is quite abstract, it's mathematical, more consistent, of course. But in my opinion, this expression here, this language here, could be interpreted in probably more directly. Look, I have to translate this language here into a block diagram language, simulating language. No? But block diagram because this is quite general. Do you remember the goal of this equation here is to express the dynamic of UC. Basically, at the end, I can say, I would like to, if you think a simulate, I would like to simulate UC. This means between UC and the derivative of UC, we have an integral with its initial condition. Remember in actuator, high school, the integral of the derivative of the function, considering its initial condition, is the function. The example which I did in actuator, the position of the rotor of the actuator is the integral of the angular velocity, calculated between 0, the time, which could be not necessarily 0, and t. This means the initial condition must be that. Now, if this is the derivative of UC, looking at this expression here, if I consider that every element UC and U input is divided by RC, if I consider that this block could represent the product between this signal and 1 divided RC, this means this signal here is exactly U input minus UC. Could be represented. Then, if this is U input minus UC, I put here in a block which realizes exactly U input minus UC. U input is an external signal. Do you remember in actuator? Minus UC could be represented by this minus here. Very important that we have a feedback, very important. This feedback characterizes the dynamical system. Or, yeah, it's the kernel of the dynamical system, because we have a dependence of my variables with UC, which is the output. Should I insist on this? I don't think so. No, in actuator, I told you a lot. Here, basically, I repeated everything, and the question at the end is try to calculate the matrix Cm and D in case I would like to represent the current. Again, the concept is the dynamical representation does not change because the energy is just the electrostatic energy. But considering different outputs to be represented, to be controlled, to be everything, the output equation changes. This means Cm and D change. Now, if the question is, if I want to represent or to describe the current, what about the matrix Cm? What about the matrix or the constant or the parameter in this case D? Again, Cm multiply UC and D multiply U input. It's nevertheless easy. Why that? Because the current which have in the circuit is C time the derivative of UC with respect to the time. This means C, which multiply everything which is in this bracket, in which we have the derivative of UC with respect to the T, which came from the structure, the structural, let me say, description. This remain fixed. But this calculation we have already seen before somehow. Huh? This is enough to multiply by C. And now it's not -1, you remember, is in 1 as before, but -1 divided R, because R, let me say, and 1 divided R remains as in a Cm, and 1 divided R remains here as D, because I don't have here C multiply R as before, but we have just C. Just a little bit to be confident, with this nomenclature and so on. Now, today, I would like to introduce a very important concept, which probably in some forms you have seen in math, which is important in our course. We will see during the semester, is the concept or the concepts of free and forced answer or answers. Again, here it was just an easy introduction about state space model, the state model, nomenclature. Again, Kirchhoff, the role of Kirchhoff in the context of dynamical system and so on. The role of the derivative, very basic knowledge. Let me now consider this part here of the lecture in which I will repeat, but with another form, the concept of, do you remember, homogeneous and not homogeneous solution of differential equation. I don't know if you remember that. Very well. Why I am considering this in this introductional lecture? Because at the beginning, what is the system, a little bit the differential equations, the form which we will use during the semester of the differential equations. And now we will see the homogeneous and non-homogeneous approach, but with another point of view. In a point of view more physical, I would like to say, probably also more in the context of system theory. We will not speak about homogeneous and not homogeneous, because this is really mathematics. We will speak about free and forced answer or answers. And the reason I will clarify now with this example, again, our example, this R system. Are you tired? No, I would like to tell you this. Let me see how many, we have time. Yeah, I would like to at least to clarify, to tell you this, and then we will see that this free and forced answer will be with us for many, some lectures, I would like to say. And next week we have 2 blocks. It could be that I'm able to introduce also today the system here with 2 states, which is more interesting. Do you have a force enough? You can start with this introduction on this concept. We will be with us together with the state space representation with different and more complex or articulated systems. Look, free answer. Basically, you know already this concept, free and forced answer, but in another form. Is an answer, or better to say the answer, I would like to say, characterized by inputs or input in our case equals 0. We can see a u in input, but the input equals 0. And initial condition not 0. Initial condition of what? Initial condition of the states. Now, in case you have just one state. UC of a time 0, not 0. It's easy to remember because free answer recalls us something which is not depending on the input. Free. I mean, in connection with forced, we can understand the input can be thought, can be associated to the force. I put here the force and the system move forced. Free means we don't have, we have input 0. But of course, in order to have an answer, in order to have an output, I have to consider that the initial condition of the energy in the system is not 0. If also UC is 0, everything is 0. No input, no energy at the beginning, 0. This means in case UC of 0 equals 0, the free answer is 0. I don't know if it's clear, this concept. No input, no initial energy, everything is 0. This means the free answer exists always in case UC, in our case, at time 0, 0, no, voltage 0 in the capacitor, no input, UC remains at 0. If UC remains at 0, the current remains at 0. UR remains at 0. Again, here in the graphical example. If U input is 0, what is the meaning? We have a short circuit. If U input is 0, we have a short circuit, right? If UC is 0, this means UC is 0, the current is 0. And UR, if you consider here, UR the voltage on the resistance is also 0. And the free answer is 0. This means that typically we say in order to analyze the system in terms of free answer, sometimes we say in terms of internal energy. Also, this is easy to understand. Internal means the internal energy, no? What we have in the UC, without considering the external energy, which is comes from U input. Therefore, we say it must be not 0, because if this is also 0, all states, in our case, it's just UC, everything is 0. It's the trivial answer, no? Or the free answer. Okay, look at this. This is the condition in our case, which can be generalized considering all inputs equal 0, and at least one state not 0. Now, we don't have here this case because we have just one state. But if you have a 2 state or 3 states, the free answer is defined considering at least one state not 0. Because again, if everything is 0, we don't have. We have an answer, free answer, but trivial is 0. Here's in a comment, no? We don't have external input, but we have internal ones, at least one. Calculations. You remember this in math? I don't know if you remember this how we can solve, no? this kind of this kind of Cauchy problem or differential equation. We have this differential equation and with this initial condition. You remember the idea is considering one possible approach, considering UC free equals a function p of t which multiply here is an exponential function. No? It's better to write exp, no? exp up to lambda t. I don't know if you remember this approach to find the solution of this differential equation, in which lambda is a constant, p of t is a function. I don't have time to repeat the theory, but you know better than me. No? And then if I calculate the derivative of this expression, the derivative of this expression is written here, in which we have is in the product between two functions. No? The derivative of p multiply the exponential function of lambda up to t plus the derivative p which multiply lambda which multiply the exponential function up to t. I don't know if you can remember this rule, no? The product of two functions. It's clear what is written here, or should I clarify this? It's okay, yeah, I think. The derivative of this expression here, which is the product between two functions. P of t is a function. P of t is a function. It doesn't matter which one. It doesn't matter which one at the beginning. Here is a little bit sketchy, but the exponential function up to lambda t. Because do you remember the exponential function is the eigenfunction in the context of a differential equation? Why that? Because the derivative of the exponential function, it itself, structurally, it is itself. Exponential function up to t, the derivative is exponential function up to t. Why this is useful for us? Because basically we are looking for something. I try to explain where this comes from, this exponential function. We are trying to find an exponential function somehow, because this expression here says I am looking for an UC free, which its derivative somehow is almost, if you don't consider 1 divided RC, the exponential function again. This recalls the concept of the exponential function, because we can see that the derivative of UC is something connected with the function itself. This is the concept of eigenfunction in this problem here. If I plug in now this expression here, and this expression here, excuse me, here, we have this. I can cancel exponential function. Why that? Because the exponential function is never zero. This means I can divide it by. And I will obtain this expression here. Oh, this expression here does not match directly, because the idea here is to find p is to find lambda. Because when I write this expression, I am assuming that the UC free, basically the function will represent the state, which reflect or represent the energy, consists of this structure here, which is the product between P of t is a function and exponential function. But of course, the goal is to calculate P of t and to calculate lambda. Otherwise, I cannot, I don't have in a quantitative form my function. Here it seems to be we are far away. But it's not totally far away, because I can try, as an approach, to consider some assumptions. We can see here the first assumption. In order to find expression for P, which will somehow simplify this equation, and in order to find the solution, I mean, what is the goal? Look at this expression here. The goal is to find P and lambda which satisfy this condition. If I am able to find this means that this assumption here is a valid assumption. This means that UC free can be expressed with this, let me say, structure. Please pay attention, assumption. This is an assumption. If I'm able to find P of T and lambda, this means the assumption is valid. This means UC free really consists on this. If P derivative is equal to 0, this means that P of T is a constant. This expression here is simplified in this form. Did you agree? If P of T is a constant, we end up in this expression. Again, consider that this constant not 0. Considering this constant is not 0. This is not an extremely conservative assumption. Conservative assumption means not a strong assumption. This is quite acceptable, because if you look at this expression here, we see that at least at time 0 is not 0. It's 12. This means this assumption here is acceptable. It's not 0. At least at time 0. Then we will see. This means we can say that this assumption is not so extremely strange. If the problem is this here, strange is in a little bit in a good word, we say not conservative, no? Because at time 0, here, exponential function up to 0 is 1, we can see that P at time 0 is 12. This means it's not always 0. It's written here, this concept. It's not 0. At least it's not 0 for each t, no? Because at time 0 is not 0. This expression here now allows to calculate lambda, because if P is not 0, or assuming that it's not 0, at least for t equals 0 is not 0, I can divide it by P, and I have this lambda, we can see I can divide it by P if this is not 0, or where P of this is not 0, I can cancel, and I can calculate directly lambda. What do we have? What we have now? We have this lambda is clear, calculated, -1 divided RC, R multiplied C, and P of T is in a constant, not 0. We have seen that at time 0 is not 0. Of course, to be precise, to be valid, we have to show that also for different value of t, for all t is not 0. Okay, let me show you this. At this moment, we have this expression. This is a constant. Let me say a constant not 0 for each time. This is the assumption when we divide it. If I divide it, here is not written, but I told you, if I divide it, this means that P of T is not 0 for each T. Otherwise, I'm able to say where is not 0. If I cancel directly, I assume that it's not 0. Otherwise, I cannot do it. Here, I didn't write everything, but I am telling you. Huh? But look, if I consider now the initial condition which I have, which is 12, we can see that this constant is 12 for each time. Why that? Because the expression where this constant comes from does not depend on t. We can see that the t is present in the exponent, but to calculate the constant, when t is equal 0, we have a constant 12, but independent of t. It's a little bit in a trivial explanation. We can use also different arguments, but let me go ahead. Probably Matt, you did something better. But what I would like to show you, this is the exactly what we already know from electrotechnic. Starting from 12, I'm going to 0 exponentially. And yeah, this came from this calculation, which basically is a repetition from mine. Let me conclude with the fourth answer. So 2 slides. And then next week we will go ahead with another example. This I already told you, no? Ah, no, the fourth. What is the fourth? How is defined the fourth answer? Now the input is activated, it's not 0, and the state is 0. Basically, this approach reflects the superposition principle, in which we have 2 causes, as I told you before. One is the external, and one is the internal. Then we will consider in a separate form, and the solution of the general differential equation will reflect the total answer when we have internal energy and we have input is the sum of both. We will see at the end that the total UC of t, or that UC of t, is this expression plus this UC forced because of the superposition principle. Because we have 2 possible causes, the input and the state, the energy inside, and then again the bank. Why my money in the bank increases? For 2 causes. I can put money forced, or I can withdraw negative input. And because I have a capital in the bank, because of the interest. You have time? Yeah. Oh, you don't have time. You have to go. Okay, if you have to go, next week we have 2 blocks. I try to accelerate a little bit, even though we are on track, considering that I will do some lectures at the end of the course, considering, let me say, some tutorial. Typically, I do 2 tutorial. This means everything is okay, but it's too fast for you, what I'm telling? Too difficult? A little bit. Come understand. We will see that we insist very often on the same concept with different, let me say, application and contexts. We will see next week. Next week we start 8:15. No? Thank you for your attention, and I hope the course will more interesting in the next lecture. Thank you.